Welcome to 7.4. We are going to use now what we've learned and practiced about and with trigonometry to now put this into action and actually use it for a task at hand by Zach. So Zach is using his knowledge of geometry to design a gazebo for his family's backyard. The gazebo will be in the shape of a regular polygon. As a part of his design, Zach will need to calculate several things so his parents can purchase the right amount of wood for the construction. For example, Zach will need to calculate the perimeter of the gazebo so he can order enough railing to surround it, and he'll need to calculate the area of the floor of the gazebo so he can order enough planks to lay it. He will also need to calculate the surface area of the pyramid, which forms the roof that will cover it. The problem is, his parents keep changing their minds about what shape they would want the gazebo to be: a hexagon, an octagon, a decagon, a dodecagon, or even some other type of n-gon. From his work in Math 1 with symmetries of regular polygons, Zach knows that all regular polygons are cyclic, meaning they can be inscribed in a circle. Zach is wondering if he can use this property of regular polygons to help him find their perimeter and area. For his first attempt at creating a scale drawing of the gazebo, Zach has inscribed a regular hexagon inside a circle with a radius of 2 inches. He is wondering if this is enough information to find the perimeter of his hexagon and the area it encloses. So, question number 1. To get started with the task of finding the perimeter of this hexagon, Zach decides to write down what he already knows about the figure. Decide if you agree or disagree with each of his statements, and explain why. You'll want to add features to the diagram to illustrate Zach's comments. So go ahead and try this on your own first. Go through on the next page. You see all of Zach's comments here. Try it, and then we'll come back together and talk about it as well. So go ahead and pause the video. Okay, let's read through this column on the left-hand side, and then we'll decide whether we agree or disagree. So, Zach thinks he knows that two radii drawn to two consecutive vertices of the regular hexagon will form a central angle whose measure can be found based on the rotational symmetry of the figure. Interesting. The hexagon can be decomposed into 6 congruent isosceles triangles. The length of the altitude of each of these triangles is drawn from the vertex of the triangle, which is located at the center of the circle, so the central angle can be found using trigonometry. Interesting. And the length of sides of the triangle that form the chords of the circle can be found using trigonometry. So, let's go ahead and try this out. First thing I want to do is add some things to this diagram. For example, I want to add those radii he was talking about. In the first statement, 2 radii are drawn to the edges of a circle, or the vertices of this hexagon. So, now that we have that, let's look at this next page. It says 2 radii drawn into 2 consecutive vertices can be found, that central angle can be found based on rotational symmetry of the figure. So we're saying we can find this angle based on the rotational symmetry of this figure, which we found out that hexagons have 60-degree rotations, right? It will fall on top of itself. This point will become this point if you rotate the figure by 60 degrees, right? So let's go ahead. You can go ahead and jot that down and say, yep, it is by saying we've got 60-degree rotational symmetry. So that's the value of that central angle. The next statement is the hexagon can be decomposed into 6 congruent isosceles triangles, which I would also believe that to be true, because if we continue around with this trend of drawing these radii to the vertices, you will see all of them are radii, meaning by definition they're all congruent, and we have 6 isosceles triangles, okay? We could also figure out that they're congruent by saying, looking at side, angle, side, right? If we have side, angle, side, of every single one of these triangles, we can figure out that they're all congruent, right? Now, the next one, the length of the altitudes of each of these 6 triangles can be drawn, or can be found using trigonometry. So now let's look at this one a little bit more specifically, okay? So I'm going to erase the rest of these. We know, though, that there are 6 isosceles triangles, right? 1, 2, 3, 4, 5, and 6, okay? So that's something important to note, okay? But they're saying, or Zach is thinking, we can find this altitude, using trigonometry. Now, how could we do that? Well, we know that an altitude goes perpendicular to the opposite side, right? And in this isosceles triangle, that means that it's actually going to bisect this angle up at the top as well. And we know if this figure has 60-degree rotational symmetry, that this whole thing right here is a 60-degree angle. So half of that will be 30 degrees, okay? So if we have 30 degrees there, we know that this is a right triangle, or a right angle, and this will have to then be 60 degrees also. So we can figure out the length of this by using some trig, right? We know that this radius is 2 inches. That was given to us. He drew a circle with 2 inches of a radius, okay? So we can figure out what that altitude is one of 2 ways. We could either say, use 30 degrees as our reference angle, and we could use cosine, because it would be cosine of 30 is equal to the adjacent side over the hypotenuse, or we could use sine of 60. Either one will work beautifully. So I'm going to just say sine of 60 is equal to the opposite side over the hypotenuse, which is 2. So 2 times the sine of 60 is equal to our distance. And when we do that out on a calculator, we actually will find that this is 1.73 inches. Okay, the altitude is 1.73 inches. Okay, the next step now is can we find the length of the sides of the hexagon, which form chords in the circle? So what they're looking at, what Zach's thinking of now is, can I find this length right here? Oops, there we go. So we can, by using trig again, we have 2 inches here. We have this one. We're not going to use that value, though, because as it's a calculated value, we round it. It's inexact. So instead, we're going to use 2 inches, and we're going to find this distance first, and then just multiply it by 2, since we have 2 halves, right? So I'm going to use sine of 30, because sine of 30 now, if my reference angle is up here, opposite is there, hypotenuse is still 2. So I've got x, sine of 30 is equal to x over 2. When I solve for that, I've got 2 times sine of 30, solve for x. And then 2 times the sine of 30 is actually equal to 1. Okay, so that means that this half is 1, and this half is 1. So now that you've got all that down, I'm going to do a little erasing so that we can have some more clarity again. Let's clean this all up. Going to leave that in there, take away some arrows. Bring this altitude back. Keep that decimal point. So if this is 1 and this is 1, then the whole distance will be equal to 2. All right? So, interestingly enough, if we examine this a little bit more closely, we actually have not an isosceles triangle, but we have an equilateral triangle, okay? So that's kind of fascinating as well. That might not always happen when we're looking at different shapes inscribed inside of a circle, but it happens in this case. Now, using that information, we have the side length of one side of our gazebo. So in order to find the perimeter then, we can just multiply that by 6. So that's our next question. We need to look at What is the perimeter of the hexagon that is inscribed in the circle with a radius of 2 inches? Well, if one side is 2 inches, one side of that hexagon is 2 inches, then the perimeter of the entire figure, because it has 6 sides, will be 2 times 6, which is equal to 12 inches. Okay? So now I want you to go ahead and describe the strategy so someone else could follow it. So go ahead and pause this video and describe the strategy that we just used. Good. Now we need to, number 3, find the area of the hexagon that Zach inscribed in the circle with a radius of 2 inches. And you can illustrate and describe your strategy so someone else can follow it as well. So finding the area, let's think. We don't really have a formula for the area of a hexagon, right? So what we're going to need to do is we're going to need to break it into smaller chunks. We do know the formula for the area of a triangle, right? Base times height divided by 2. So what we can do is we can actually use that, find the area of one triangle, and then because we have 6 congruent triangles, we can just multiply it by 6. So let's try that over here. All right. I have the base of that triangle was 2 inches. The height of that triangle, the altitude, was 1.73 inches. And I need to divide by 2. Well, interestingly enough, 2 and 2 cancel off. So the area, and let me just denote here, the area is equal to 1.73 inches squared. Okay? So that's kind of fascinating, but that's the area of only one triangle. So in order to find the area of the entire hexagon, we need to multiply it by 6. So when we do that, we actually get 10.38 inches squared. Okay, so that is the area of our entire hexagon. Okay, so now go ahead again, describe the strategy so someone else could follow it. All right, now there's a little bit of a tricky part here. We are going to look at if someone else had it, or excuse me, if he had inscribed instead an octagon rather than a hexagon. So let's try to figure that out, okay? First thing we did previously on the last page was we determined the angle of our central angle there, made by 2 radii drawn. So let's go ahead and try that as well. Here. So I'm going to draw that first of all. Okay, now I need to know what that angle is. Well, how many of these triangles could I draw? I know that surrounding this entire thing is 360 degrees, right? So if I know that that's 360 degrees, I can just look at how many triangles I will draw and divide 360 by that many triangles. That will give me the degree measure of one angle, central angle. So I've got 1, 2, 3, 4, 5, 6, 7, 8. All right. Kind of makes sense since it's an octagon, has 8 sides. It's going to also have 8 central angles, 8 triangles there. So let's take 360 and divide it by 8. And when we do that, we can find that it equals 45 degrees. So now we have a triangle here with 145-degree angle, okay? Now, what did we do again before? We need to look back at the other side, and we then figured out, okay, what is the altitude? Because we need the perimeter, and we need the area of this thing, right? So let's look back at what we did on the last page. Oops. Oh, I erased some of it, but I used trig, right? I used trigonometry to figure out what the other side lengths were, both for the base and for the altitude, okay? So again, I divided this central angle here in half, this central angle. So now instead of 45 degrees, when I divided it in half with that altitude, half of 45 is 22.5. Okay, so now that's going to be my angle that I'm using with trig instead. And I still know that this is 2 inches, right? So to find this height, this altitude here, I'm going to go ahead and use some trig right? I have the adjacent side of my reference angle and I have the hypotenuse, so I'm going to use, so cosine is equal to the adjacent over the hypotenuse. And actually that's kind of confusing for that to be labeled h, so I'm going to label it a. So I will have cosine of 22.5 degrees is equal to the adjacent side over the hypotenuse. Okay, so then I will just have 2 times cosine of 22.5 equals a, and when I actually multiply that all out, I will find that it is 1.848 inches. Okay, so just a little bit longer than our last one. 848. Okay, cool. Now let's find the length of the side of this octagon. Okay, and I'm going to do that very similarly in the way that I just did, except for instead of using cosine, this time I'll be using so, the opposite over the hypotenuse. So let's say sine of 22.5 is equal to the opposite side over the hypotenuse, which is 2. Here, let's call that x. Sorry, my variable game is not strong today. And this will be 2 times sine of 22.5 equals x. So now when I multiply that all out, I will actually get that the side length is when I multiply it out and multiply it by 2, I get that the side length is 1.531 inches. And that's for this whole side length, 1.531. Because I just multiplied it by 2 again, because I'm looking for both of these pieces here. Okay? All right. Now that I have that, I can find both the perimeter by multiplying by 8, and I can find the area again, right? So I can find the area the perimeter by saying 1.531 inches times 8 sides, and then I can find the area by saying by saying 1.531 times the height of the triangle, the altitude 1.848, divided by 2, which is the area here, so this is perimeter. And when I multiply and divide both of those out, I get up here 12.248 inches for the perimeter. And below, I get 11.317 inches squared for the area. Okay? So now we've done it for a hexagon. All right, we had to modify our strategy just a little bit, but we've done it, for an octagon, rather. All right, so now we need to modify our strategy to find the perimeter of any regular n-gon. Okay, so it's a polygon. That's another way to say polygon. So we're going to use the exact same approach that we did previously, but instead of using actual numbers, like for this central angle and everything, even the way that we found the central angle here, when we divided by 8 and divided by 6, 360 by 8 and 360 by 6, we're going to use variables, okay, based off of the number of sides. So n is our variable that equals number of sides. And yes, that is a number sign, not a hashtag, not just hashtag of sides, okay? So for the number, to find the central angle right here, that's going to be 360 divided by the number of sides that we have. Okay, that's how we found that central angle. All right. So in order to find the angle, once we have made the altitude, remember that it cut that angle in half, right? So our new angle there is going to be 360 divided by n times 2 on the bottom there, because we divided this in half, right? Then we'll figure out, okay, what is the length of the altitude? Well, I don't know what the radius is. I'm being very general here. So I'm going to actually use r as radius, and now I need to find the length of the altitude here. So in order to find the length of the altitude, what we did is we used trig, cosine of 360 divided by 2n, right? Divided by, or the trig of that central angle there. And then I'm going to multiply that by r. That's what I did every time. Okay, now I need to find the length of my chord, right? This piece of the polygon, the side of the polygon. And the way that I did that was, instead of using cosine, this time I used sine of that central angle that we divided in half. Okay, and I multiplied it by the radius using the trig ratio that we had discovered. And then I multiplied it by 2 because that was only finding out 1/2 of them, and I needed to find out both of them. Okay. Now the perimeter, then, we're going to use that information because that's the length of one chord. So we're going to use that information to figure out what our perimeter is, okay? So to find the perimeter, we just multiplied this by the number of sides that we have. And again, the number of sides we have is n. So we're going to do n times 2 times r times sine of 360 over 2n. Okay, so there's the perimeter, and finally we're going to find the area of the entire figure. So the first thing we have to do is find the area of one of the triangles, and then we will be able to multiply that by the number of sides to find the area of the entire figure. So the area of one of the sides was 2 times r times sine of 360 over 2. Right, 2n, excuse me, because that's the length of one of the chords, one of the sides, okay? And then we're going to multiply that by the height of our triangle, which we found by going r times cosine of 360 over 2n, okay? And then that will give us the area of the triangle, almost. We have to then also divide it by 2, right? And now, if that gives us the area of one of these triangles, we can multiply that whole thing by the number of sides that we have. Okay, and that will tell us the area of the entire figure, no matter how many sides it has. So then, this can get a tiny bit simpler. So what we're going to look at is the 1/2 and the 2 cancel off. And then the r's come together, so we can say n times r squared times sine of 360 over 2n times cosine of 360 over 2n. Okay, so we just basically created the abstract formula for how to find the area of a polygon, okay, any polygon, regular polygon inscribed inside of a circle, when you know the radius and when you know how many sides it has. So there you have it. Good luck on your RSG.